Over time, the seismic norms have increased the seismic forces, and then we need to find some kind of solutions to, let's say, reducing the loads and produce more, let's say, economic structures. Starting with the 2000 years, the applications of various solutions to reduce seismic forces in the structures have been started to be applied in Romania. At the beginning, let's say, at a lower scale, and after that, becoming, let's say, a current practice in the design. I would like to present you four structures. Let's say, I'm sure that there are many other examples, but these structures are, let's say, from our experience, let's say, somehow different from what is currently done in Romania. There are four structures. One is the overpass at kilometer 0 in Craiova, which is completed. Another one is a bridge over Pișuret at the river in Oradea, which is also completed. Then it's an overpass in Bucharest ring road, which is under construction right now over DN2. And the last one is an interesting solution for a footbridge at Curtea de Arces, which is, let's say, the design stage is not finalized, but let's say we have some let's say, advanced stage. Okay. Okay. The overpass at kilometer 0 of Craiova, it's okay. The bridge is having a total length of around 300 meters, and it's having 8 spans. It's a continuous structure completely, and also is in plane. It's placed on different curves. The superstructures is supported. The superstructures. Okay. The superstructure is a complete prestressed box which is having four webs, two exterior, two interior, and it's supporting 2 traffic lanes and also 2 tramway lanes. The tramway lanes are also possible to be used by the traffic as well. The main problem of the bridge at the time of the design, which was around 2008-2009, was that the bearings were at the time chosen like pot bearings, and as you know, pot bearings are of 3 types: completely fixed, or unidirectional, meaning that it can displace in one direction and is free in the other, or completely free. And the bridge is not, let's say, in a very high seismic area. At the time of the design, it was seismic maximum acceleration of 0.16 G. Now it's 0.20. But still, the weight of the superstructure was quite high, and the bridge being continuous and the pot bearings being, let's say, the nature of them, we can have only one bearing which is completely fixed on the structure. So the problem was that the seismic force couldn't go to a single substructure because it is obviously too high for that. The solution for the bridge was to provide some connectors which are placed on each piers. Connectors which are not exactly dampers, are only connectors, meaning that during the seismic force, they will block the movement and will allow all the substructures to take the seismic loads, while in a normal service, they allow for the movement due to the temperature and other forces. This is the, let's say, the drawing for the bearings. It is not so easy to see, but anyhow, there is just one pier, I think pier 4, which is having fixed bearings. All the others are unidirectional bearings or free bearings in the longitudinal direction. Okay, at the time this was the solutions to use ball bearings and connectors. Now maybe if some, let's say, improvement it's needed there, we can, let's say, change the type of bearings to, let's say, LRBs, which are probably improving the seismic behavior. These are the images for the completed bridge. In the top right, you can see also the connectors on those piers. The second bridge is a bridge over Crișu Repede at Oradea, which is not a very, let's say, big structure. It's only 80 meters between the abutments, actually a little bit less than 80. And this is the solution that was, let's say, approved by the client at the City Hall of Oradea. And it was made, I think, during some kind of contest, of architectural contest. And they choose this kind of solution. We, as you can see from the drawing, the arches are completely blocked, fixed into the abutments. So no kind of movement is possible from the initial design. When we went to, at the next stage of the design, we went into, let's say, more detailed calculation. We saw that we have a problem because actually the first vibration of the period of the bridge was exactly the same with the corner period of the area in which the bridge was located. And the good point was that this vibration was also in the transversal direction. So the bridge is not located into a very high seismic area here, or rather is not something very special, but still this kind of matching, we didn't want to leave it like this. And the idea was to introduce a transversal damper into the at the abutment, a connection between the arches and between the arches and the abutments, which only works in the transversal direction, meaning that we developed some kind of device in order to keep the arches blocked into the abutments on all degree of freedoms, except the transversal one, which was actually blocked by this PDS. During normal operation, this PDS is completely fixed, it's not allowing the structures to move. But during the earthquake, there is a fuse there, and that will release the damper, and the bridge will be possible to move in the transversal direction. You can see here how it was done. You can see the crossbeam between the arches and the damper behind under the bridge. And these are the images from the, let's say, inauguration. The bridge is called Podul Centenarului because actually it was inaugurated on the 1st of December 2018, after 100 years from our reunification. This is a, let's say, interesting design which we did in cooperation with Fresine. Actually, it's not our idea, it's theirs. It's a footbridge at Curtea de Argeș. It has a maximum span of 170 meters, as you can see, the marginal spans are only 31 meters, and they are, at the end, they have some kind of counterweights, which are blocking the superstructure and taking some horizontal forces and also vertical forces. There are only two backstays, and these counterweights are actually some kind of boxes. You will see in the next slide, which are, let's say, filled with gravel, and there is an anchorage for the backstays. And what is interesting here is that this, let's say, huge counterweight is supported only on 6 piles of 1.2 meters the diameter, and these piles are not directly connected to the counterweight. There is a connection through some bearings, LRB bearings, which are between the piles and the counterweight. This allows us to reduce the seismic forces and have some kind of, let's say, better reinforcement into the piles and a better behavior of the bridge. There is also a damper which is helping the LRBs. You can see it in the tensioning chamber. The last one is an overpass on Bucharest Ring Road over National Road number 2, which is actually under construction now. The bridge is not, let's say, something very unusual, only that instead of the cross section is with 4 precast pre-stressed beams executed by ferrobeton. And actually what we did here is that we made the structure continuous on 3 or 4 spans, because the full bridge has around 8 spans, and we divide it into two separate structures of 4 spans each. And we have reduced the number of bearings because we have only 4 bearings on each substructure instead of having 8. And in order to reduce the forces into the substructures, we also provided LRB bearings instead of, let's say, normal bearings, neoprene bearings or some other. Other than that, the bridge is quite normal, and there is nothing special with it. Here there is a diagram for the behavior of the LRB, which is provided by a Chinese company, the bearing itself, and that's it. Thank you for your time.